In this video, we're going to look at two independent population proportions. So we're still comparing two sets of data. This time we're looking at population proportions, so we're looking at successes out of the total sample that we're looking at. We will be using P prime, you might see P hat, you might see P bar. And we have the first proportion, and then we have the second proportion. So there's a couple of things that has to happen for us to be able to use this. This is kind of like the binomial, so there are some requirements. So the first thing is that we're going to be using a z-test. The two samples are binomially distributed. They are independent, simple random samples. And there are at least 5 successes, so that means x must be equal to n times p, and there are at least 5 failures, which is n minus x must be n times q. Sometimes you might see this as n times p has to be greater than or equal to 10, and n times q has to be greater than or equal to 10. And sometimes you see this as n times p times q has to be greater than or equal to 10. When comparing two population proportions, we are of course interested in the two sample proportions. This is where the p prime, p hat, p bar comes from. And it's going to be equal to the x sub 1 divided by the n sub 1. And the p2, of course, is going to be the x sub 2 divided by the n sub 2. So this is the number of successes out of each sample. So x1 being the success for the first sample and n1 being the sample size for the first sample. Now when we are doing this, we do a pooled proportion. We call it P sub C. This will be the sum of the successes of each sample divided by the sums of the sample sizes. So again, this is something that we will need to put into our spreadsheets so that we don't have to do that calculation each and every time. The distribution for the differences of the sample proportions can be approximately normal. So we have P1 prime or P hat 1 or P bar 1 minus the P sub 2 of bar hat prime, and it'll be approximately normally distributed. Now notice how this has changed. It goes from P1 minus P2 instead of just being P. And then we have P sub C, this is our pooled proportion, multiplied by 1 minus our pooled proportion. So this is like our Q for the proportion. And then we have 1 is going to be multiplied by 1 over the first sample size plus 1 over the second sample size. And again, we will have our spreadsheets do this. The z-score looks something similar to like we did in 10.1. We have the P1 minus the P2, and these are from the sample success as proportions or decimals, minus the P1 minus P2 of the sample, or excuse me, of the populations. As before, we are going to assume the population's proportions of the successes to be the same, so we are going to have a 0 be in here, so we'll have a 0 here, and then our standard deviation is this calculation. When we are doing a hypothesis test in two populations, usually the claim is that the proportions are equal, or the one group has the higher or lower than the other. And so our claim for the comparison of proportions H naught would be something like this. H naught is that they're equal to, H naught is that one's greater than or equal to, and H naught is one is less than or equal to. That means our ha will be the opposite of each and every one of these, kind of like we did in our previous example with our means in 10.1. Let's take a look at this. First example, there are two types of phone operating systems that are being tested to determine if there is a difference in the proportions in terms of their failures or crashes. So success actually is crashes or failure. 15 of the random samples of 150 phones had failures within the first 8 hours. 9 of another random sample of 150 phones with this other operating system had failures within the first 8 hours as well. OS2 is believed to be more stable and have fewer crashes than OS1. Complete the hypothesis test at an alpha as being 0.05 significance level. So we know that right out of the gate, this is the proportions because they're giving us the failure out of the total. So this is proportions. Are they independent? The answer is yes, because they are two different operating systems. Our random variable here, so this is a proportions. They are yes here, and the random variable is either capital P prime or capital P bar or capital P hat. So then what is the null and the alternative hypothesis? So to make our lives easy, P1 is for OS1 and P2 is for OS2. Now, we believe SO2 is believed to be more stable. So what we believe is that P1 will have more crashes. Now remember, success is crash. So my HO is that P1 will be less than or equal to P2. P2 will be more stable. So this will have more crashes than this one. And then my HA is that P1 is greater than P2. Again, this is because we actually believe the success, which is the number of crashes, is going to be less on P2 than it is P1. So this is what we are claiming. This is what we're hoping to prove. And this is the status quo. We can actually use 0 equals to as well. It doesn't matter if we do less than or equal to on this, because it's really the HA that determines the test. And we can tell on this because the inequality is pointing to the right. It is a right-tailed test. What kind of distribution is this? This is, let me go ahead and scroll up a little bit. We know that this distribution is a normal distribution where I have the P1 minus the P2. You can use hats or primes, is approximately a normal distribution. This will always be 0 right here, it's like we talked about before. And then here we're going to have the square root of P sub C multiplied by Q sub C, and where Q sub C is 1 minus the P sub C. And then, of course, this is going to be multiplied by the square root of 1 over the sample size of 1 plus 1 over the sample size of 2. And that's not a square root. That's just a, let me erase that. That is not a square root. Square root's on the outside. It's just 1 over N1 plus 1 over N2. Square root's over the entire thing. Okay, so I am going to go do a p-value, but let's talk about how I get there. I'm actually going to talk also about the critical value, and we're going to talk about the test statistic. I know it doesn't ask for it, but it's really nice to have that kind of information. So here's the calculator that you are going to build. I like to label everything. So I like to label everything. What I didn't label is what I should have labeled is Q sub C, which is 1 minus the P sub C, and that is my pooled, if P is success, then Q is the failure. So this is my pooled failure. Failure in this example actually is our success, which that doesn't mess with you. I don't know what does. Now these numbers are not the numbers that are up above, but I do want to talk about how to enter this in your calculator. So alpha divided by 2 is calculated. Again, if I see lowercase, that means I am going to grab the cells that have the alpha, and then I'm going to divide that answer by 2. So in this, I would have done an equals. I would have grabbed the cell. I would have divided by 2. These are values that we are going to put in. Now, why do I have the denominator of P1? Well, sometimes what's going to happen is that they're going to give me a percent. So they'll say 50%. So I'd put a 50 here, and then I'd put 100. And then this may not be 100. It may be, say, 72 pieces of data. So this helps me do any kind of conversion in which I may or may not have it as a decimal. So again, if I am giving, say, 25% as an X sub 1, and that's actually my P sub 1, but I want everything to be calculated, so it actually is going to calculate it here for me rather than entering it. So if they give it to me in terms of success numbers out of total, then I would put the success number out of total, and then I'd put the total again right here. If this is given to me in terms of percents, then I would put, say it's 25%, I'd put 25 here, 100 here, and then I would put whatever my sample size is here. And the same thing is happening here. Now you can see that I tell you to enter these values, and the reason I have 2 different colors of greens is, and I should have actually done on my other spreadsheet, is so that I can see this represents my X sub 1 and this represents my X sub 2. Now notice that my P2 is the X sub 2 denominator. Now to get my pooled, I'm going to do my x sub 1 multiplied by my p1 plus my x sub 2 multiplied by my p2. And these p's are the primes. They are p1 prime and p2 prime, or bar or hat if you like. And then it's going to be divided by. Again, I want to remind you that these are lowercase. So in this cell, I would have done an equals, and I would have grabbed the cell that had the x sub 1, did the multiplication symbol, grabbed the cell that would have had the p1, and then plus would have grabbed the cell that had the x2, multiplication symbol, grab the cell that would have had the p2, and then the division, and again, grabbing the cells that have that. Now, once I get down to all of those calculations, I then see here that this is the norm.invert. So in this cell, I would have done an equals. I would have typed in norm.invert. That is a call or a function within Excel. And then I would have grabbed the cell that has alpha divided by 2. I used 0, 1. And in here, because this is a normal standard distribution, you could have done norm.s. And then you would have just had to grab your alpha divided by 2 cell or your alpha cell instead of doing the 0, 1. Here, it doesn't really matter. And once again, I am going to find my z-score. Here's my z-score. This could be negative or positive. Just remember that if it is negative, because it could be calculated as negative, and you are a right-tailed test, you'll need to adjust for that. Actually, it shouldn't be negative if it's a right-tailed test. It should be positive if it's a right-tailed test. And then, of course, we have our left tail, right tail calculations. I'm using the norm.dist. I'm grabbing the z-score that is calculated. This is my calculated z-score. Now, remember, these are my critical values if I have one tail or a two-tail test, and I slap it on the plus where I have a right tail, so this would have been a plus. This, of course, is my calculated test statistic, and then here's my values. And then I would put in my appropriate p-value here. Now, you notice on this, I didn't actually grab and put in the appropriate one. So say that it is this example, not the one up above. Say this example was a left-tailed test. I would have grabbed this and I would have put the 0.54, so I would have put that number in right there. So that is the spreadsheet. Now let's go back to the example. So I'm going to go out to my spreadsheet. I'm going to put the numbers in the appropriate places. Please make sure that you are getting these same numbers in your spreadsheet as I go through this. And the p-value that I got was 0.10. This is my p-value. My test statistic, which is my calculated z-score, so z of p1 prime minus p2 prime. This is my test statistic. I got to be 1.277. My critical value, which is my, in this case, happens to be the z-score of alpha. I calculated to be a negative, but remember I am right-tailed, so I choose the positive, so it's 1.645. Now, a couple of things here. Remember, this p-value is larger than this, so we're going to fail to reject. And of course, this test statistic, comparing it to this critical value, this one is between the critical value and the proportion, the mean, the middle part. So the decision is fail to reject, fail to reject. And that's because my p-value is 0.1, which is greater than my alpha, which is 0.05. And so I would write something along the lines that there's not sufficient evidence to support the claim that OS2 is more stable than OS1. And that's it for this video. Nice little short one too.